All right. Well, I'm going to talk about high-performance computing with two of my fellow colleagues at Docker, Christian and Christine. Did I say that correctly? Yep. Please give them a warm welcome, and I'll hand it over to them.
Yeah, hi everyone. We would like to talk about accessible high-performance computing for everyone, which includes GPUs and all the other good stuff that's in HPC, and how we do it with Docker and containers. And this is not like a project that we provide, like an open source project. It's more an internal discussion that we externalize a little bit. So we let you have a sneak peek into what's going on within Docker and how we are pushing this forward. So, Christine?
Yeah. Hey everyone, I'm Christine Lovett. I'm a solutions engineer on the public sector team. So I work with a few different agencies and groups of agencies. I work with kind of both ends of the technology adoption spectrum. I work with state and local governments who are typically more risk averse, much less likely to be trying out new technology. I work with higher education institutes, so they are much more progressive and research focused. They want to stay competitive in the market. And then I work with scientific federal agencies, so NASA, NOAA, NCAR, UCAR, who are much more progressive and are, concerned with compliance and everything, but much more likely to adopt really innovative technology to support their missions.
All the nice and all these nice acronyms, right?
Exactly.
And I'm Christian. I'm a technical account manager at Docker in the EMEA region. And I work with strategic big accounts in the DACH region, basically. And in a prior life, I was in the HPC community for a couple of years, worked in the automotive industry. And ever since I encountered Docker 4 years ago, like 0.7 was the version, I think, I tried to match HPC and containers. And now that I'm working at Docker, it's much more momentum behind it. And it's much more fun, actually, to have Docker in the business card than some other company. So that's cool.
Yeah, so let's talk about the driving cases in high performance computing. And actually, before we get into everything, can we get a show of hands for who's working in HPC right now? And yeah, awesome. Wow, what's up?
And GPU, like non-HPC, but GPU, like AI and deep learning?
Great.
Yeah,
Cool.
A couple of, okay.
There. So HPC is solving some of the most critical problems in our world today. Everything from stockpile stewardship, so making sure that we're reliably testing and maintaining nuclear weapons without actually testing nuclear weapons. Computational fluid dynamics, so branches of fluid dynamics solving problems involving fluid flows. So think aerospace and defense, automotive research, bicycle research, really anything that involves fluid dynamics and making things more aerodynamic, essentially. Genomic sequencing, so DNA sequencing has become a really big technology in biology and medicine, anthropology. In 1990, the Human Genome Project took an international group of scientists to map all the genes of the human genome, and it took 12 years. Now we can map up to 8 human genomes on a supercomputer in one day. So the technology is really advancing all of these use cases and is enabling us to do personalized medicine, which is going to be really powerful for more targeted cures. And then life sciences, and then, let's see, what else did I have on there? So financial irregularities. So using HPC to determine if there's any fraud or suspicious activity in the financial markets can be done with high performance computing. So a wide range of use cases, but the one that we want to really focus on today is we think the most important problem of our time, which is climate change. So we're using high performance computing to really understand and solve this problem. So climate change, I'm sure everyone in this room agrees that it's a real issue, and it's likely the result of human activity over the last 70 years or so. So what's really concerning is that this is continuing to proceed at an unprecedented rate over decades to millennia. So it's something that we really need to understand and address. So what you're looking at here is a simulation running in a container that Christian put together with some help from Jupyter. Essentially, these are just tools that can understand weather patterns, how all of the different elements in our climate and Earth really affect ourselves. So how can we respond to climate change? And to do that, let's look at it through the lens of time. So looking at the past, addressing the problems in the present, and then thinking ahead to the future. So looking at the past. So I just like space because it looks cool. So we've got Earth orbiting satellites collecting data about our climate and our world. So this is helping to inform us about the state of our climate. So NASA and NOAA, all those agencies that I rallied off before, they're collecting all of this data about our climate and leveraging big compute against big data to make sense of the changes in our world. So we're seeing warmer oceans, shrinking ice sheets, glacial retreat, rising sea levels, extreme weather, like very positive things. So we need to address this all. And so how do we respond to natural disasters today in IT? So this is where I get back to thinking about the state and local governments. When I'm working with these customers to help them understand how they're going to implement their container services, the top ask is always around disaster services for their constituents. So being able to have a disaster recovery plan if there's a hurricane that rolls through in the state of Florida, making sure that those emergency services are going to stay up and available for their constituents. So last year we saw major devastation with hurricanes in Puerto Rico, in Florida, Houston. So if you're a vulnerable place like that, you want to have the ability to burst your emergency services into the cloud, and that's why containers are so powerful. They're also leveraging real-time monitoring social media for emergency response, but what we really want to do is kind of guide these organizations who are typically less innovative to embrace new emerging technology so that they can better prepare their communities for natural disasters. So we want to understand the past, respond in the present, and prepare for the future. So we think that containers are such an innovative, powerful tool, and that they can really foster interest and build skills in the next generation so that they feel empowered to solve these really hard problems. And now Christian's going to talk about the technical makeup of what HPC is.
Yeah, thanks, Christine. I want to break down a little bit how high-performance computing works in general. So we talked about weather and climate simulations, which are rather complex, of course. And I brought it down to a little computational fluid dynamic simulation, which you see here on the three little pictures, with a starting condition on the left-hand side, where you just have a little, or not so little, body of water that stands on the far left of the picture. And when we release this body of water, it will crash into this little knob, this little dam. So the simulation is called dam break. It will crash into this knob, and then it will flow over this little dam. And to make this computation work, we need to chunk up the time in little discrete portions. Let's say this one step has 50 milliseconds, and I just made it up. And with every iteration, we start with a starting condition, so with this picture that we see here, and then we iterate, or we simulate this 50 millisecond time step, and the end results of this iteration will be the starting condition for the next iteration. So you cannot compute the last iteration, of course, without computing all the iterations before, right? So you need to compute this in sequence. And moreover, if you want to compute this on multiple processes, multiple cores, you need to chunk up this little domain into multiple smaller domains. So you decompose this problem in multiple little domains, and then you can put them on different cores or even on multiple nodes. And I made this, of course, up as well. I chunked it just up in four equally sized rectangles, where the right-hand side, like the top one, won't do much, so that's a little bit stupid, but that's the basic. Like, just chunk it up, and you can optimize this chunking, but anyhow. Okay, and so we have these iterations, and each domain will compute the iteration that's currently working on, and at the end of the iteration, it will exchange intermediate results with all the neighbors, right? So that they can compute the next step. And this means as well that you have to compute all the domains at one time, and then it iterates through all the other domains. So you cannot just let one core go off and simulate all the complete problem. It's always that one iteration has to finish, all of the domains have to finish, and then the next iteration can start. So the weakest, the slowest node, the slowest core will define how long the simulation will run at the end. And fitting this on one compute node is rather easy, right? You have shared memory, so you can exchange the results very fast. But if you want to compute it on multiple nodes, you have first this jitter in between different compute nodes, as well as the problem that you have to exchange these results rather fast. So that's why the community came up with a lot of cool technology like InfiniBand, which was my love child a couple of years ago. Or I liked it. And InfiniBand and Rocky and all these cool standards where you have a very powerful and very fast exchange of results with these technologies. So if you have a couple of nodes or hundreds or thousands of nodes, All of them need to be very homogeneous so that you have the same computational speed so that you don't have to wait for a slow compute node. And then you can spread this out on a lot of nodes. And here I have a little brief history of HPC, and this slide could be an hour in itself, but I want to keep it a little shorter than that. So we have the names of the supercomputers at the top, and on the bottom in parentheses, we see the computational power of the systems. And the flops is floating point operations per second, and you have like millions, so mega, so that's billion, or gigaflops, and we will see the other tera and petaflops at the end. So this is a computational power. And the first system we see here is in the 60s, a CDC 6600, which was much cheaper than the system that was used before it, but it was 10 times more powerful. So it cost 8 million, and the IBM that it overtook was 13 million. So this really sparked HPC back in the days because it was more accessible and easier to use. And the following systems, like we see the Cray, that ended up with the Cray 2 at 2 gigaflops almost, that went further and further. Then the Japanese stepped in with 600 gigaflops, and to put this in perspective for today's compute powers, with your workstation, your MacBook Pro, you might have an Intel Core i7, and the biggest one has roughly 200 gigaflops. And if you go to Amazon or you buy a server from some vendor, the Intel Xeon Platinum has about 3 teraflops. So this were in the 70s, in the 90s, we had like 600 gigaflops, which is roughly the ballpark. And going further, the ASCII Red was the first microprocessor-based supercomputer, which broke the barrier of 1 teraflop. And then we had the advent of Linux, overtaking all the big systems in the world. All the systems, they are mostly running Linux, like 99% of them run Linux now. And this was the first system that brought Linux to the table. And with the Earth simulator and Blue Gene, we had the 2 digits teraflop area. And to put this also in perspective to today's computers, we have NVIDIA's box, the DGX2, which costs you only 400K. It has around this ballpark of computational power with 64-bit floating points. You can reach 200 teraflops. And all these AI workloads, they do not need as much precision, so you can have integer with 8 bits. And with this, you have 2 petaflops even of compute power. So that's a crazy amount of compute. And leading up towards today, we had the Roadrunner, was the first system reaching the 1 petaflop era, that's AMD's Opterons. And the Chinese entered in 2010 with the system. Then the Americans, the Cray, Titan, was the first one to introduce GPUs to the systems, or to the top 500 list. And now we are at a stage where the current fastest system is the Chinese Tehu Lite with around 100 petaflops. And a couple of days ago, like Friday, Oak Ridge and IBM announced that they have the new IBM Summit system, which has a peak of 200 petaflops, but a sustained aggregated performance of around, I think like it might be 150 petaflops, but I don't know the number, so that's a guess. Yeah, and this concludes the little brief history of HPC. And the new kid on the block, of course, are GPUs, and we saw this with the Titan system there. And CPUs have rather complicated cores, right? x86, and you have maybe dozens of them. With GPUs, you have hundreds or thousands of cores on your disposal, and you can crunch a lot of data at a very parallel manner. So the advent of GPU computing enables new use cases, and in particular, I think one of the cool kids on the block is now deep learning, where you can train a neural network to figure out whether it's a dog or it's a cat. I mean, that's a famous one. Or you use it for autonomous driving, of course, and all the cool stuff that's going on. And this is just enabled by the sheer power of GPUs, which you cannot do really on a CPU. Yeah.
My side.
Then go ahead.
What does this have to do with containers, right? So you have a good understanding of what HPC is, what it's used for. So let's stick with this multi-layer approach to see what we're practically addressing in the past and the present and the future of climate change with containers. So SciOps, we can't coin this term, but it's kind of like DevOps. So this is a very simplified view, but essentially we're looking at how containers can enable scientists to be more efficient, just like we've enabled developers to be more efficient. So our scientists really should not be systems administrators, but they've turned into that. They've got to be very familiar with software configuration, be able to run software, be able to replicate it and share it with other people. Yeah. Oh yeah, you better sacrifice.
Sorry.
So it's helpful to understand this workflow, right? So typically you have a researcher who is running on their current workstation, running models, testing different data to fine-tune things until they're confident they've got the results that they're looking for. And then at that point, they're going to send it to be peer-reviewed or collaborate with other scientists or researchers on that work. And so this is where containers become so important and so valuable, because it now makes these workflows and workloads reproducible, so that they know, okay, I ran this in a container on my machine. I know that when I send it to Joe or Susan to my left or right, that it's going to run the same on their workstation as well, so that we can collaborate and iterate on these models without having this dependency hell that everyone's used to facing in the normal software environments. So this becomes really valuable, not just from an ease of use and reproducibility, but it's important for science too. You want to make sure that the models that you're running, it's accurate. So if you're using an old package or something, it could throw off your entire output. And so this is a way to ensure that what's being reproduced is actually as it was meant to be by the original person. And then when it gets time for that work to be sent to a supercomputer, you know, you've received your grant and you're going to run at Oak Ridge for 6 weeks or something, being able to package up that simulation in a container makes it much easier to get to that last final stage of the process. So ensuring that you can run on a high-performance compute node with the package that you've put together is very valuable. And we're not fully there yet, but we're getting there. And we were speaking to someone today who brought up an interesting point too, from the perspective of a airline manufacturer. I'm just going to duck down here. An airline manufacturer. So if they're using HPC to, you know, develop a new jet engine or something, and then 10 years down the line, there's a major flaw, and you know, the plane went down or something. Being able to go back to that exact model that they ran to develop that hardware or that engineering work can help with root cause analysis. So there's a plethora of benefits to that reproducibility.
Yeah, to this point, like 10 years ago, we had Red Hat 5 or whatever, and running code that's supposed to run on Red Hat 5 on Red Hat 7 is most likely to fail. And with containers, you can just package this up, right? And we know this, like with DockerCon. So you can package it up and you can run it. Since the kernel is a very stable ABI, we can run it 10 years later. I mean, we didn't try because Docker is 5 years old, but should be able to run it in 10 years without problem. Okay?
Cool. And so let's bridge this technology gap. So how can progressive entities or non-progressive entities leverage this technology? Typically, high-performance computing has very high barriers to entry, so you need to have hardware expertise. As Christian mentioned, there's very special devices that are used in these environments that aren't typically found in your normal data center. And then there's software expertise, so you need people to understand and be able to run and operate the software, and it's extremely costly. So some supercomputers run $500 million. So Miami-Dade County is not going to go out and buy a supercomputer tomorrow and then have to replace it every 5 years. It's just not reasonable. So being able to bring this technology to entities that typically wouldn't be able to adopt it is really powerful. So we can leverage cloud providers and small HPC cloud providers who have this technology in their portfolio, and then containers and the portability of containers to kind of bridge that gap. So they could say, maybe New York City just had a new, a tower built or something, and they want to simulate flooding over the river. So now that they can, do a 3D model, run some CFD, computational fluid dynamics against that, without having to invest in any infrastructure, any real-life testing, or any of the technology that we're talking about here today.
Yeah, and to this point also, just adding things, we were approached by a little university who wants to collaborate with a big university to do HPC on site, right? And they have now, they don't have the headcount and not the expertise to spin up an HPC system on their little university. So they want to collaborate with a big university, and how better to do it, like having Docker EE run there and Docker EE running there, so that you can just exchange the containers and the workflow, and then off you go. And you don't need the expertise of a big supercomputing site to have your own HPC system anymore. So you can scale it down to very small chunks. So that's pretty cool as well.
and prepping the next generation. So this is to tease anyone with kids in the office that's doing like a glowing pickle science experiment. I didn't investigate, I don't know what that is, but so now that this technology is becoming much easier to consume, we all know how easy it is to spin up a container. I don't know how to run these programs, but I know that if I can get a data set and follow documentation, I'll be able to create some results. So we can make this kind of technology available to students, high school age, college age, and get them really interested and excited about the technology. And that's going to really prop up our next generation. So we can kind of get away from this like fundamental dinky-dinky stuff that they're doing in science classes and get them onto more tangible, effective ways to get involved in science.
We'll get a shitstorm. Anyhow. So as I'm about to do a demo, I just forgot to have this little thingy there. But it says, we'll bring you live by containerizing existing applications with Docker Container Platform, and that's basically what we are doing, so it's perfectly fit. Hopefully the demo god won't mind that I did it later. So we want to look at how HPC now utilizes containers at the current stage, and we can all agree, I think, on that the build and ship is a done deal, right? We use Docker files, and everyone else uses Docker files to create containers, and then they ship it to Docker Hub, or maybe they have their own private registry, so they ship it there, and then you can use this Docker images from there. The problem and this is like a thing in science, in HPC sites for a couple of years now. With the advent of Docker, they started to containerize their system and run it on their workstation, their laptops, and then they approached the IT folks, the ops folks, and said, look, I have this cool container here, I want to run it on your supercomputer. And they said, nah, no, cannot do it, because back in the days, Docker CE was not that mature as it is today, or with Docker EE even better. They were very reluctant to run a single root daemon that is able to spawn containers and spawn processes on the system. And there are other things, like the workflow that they use, and I will show this in a bit, was not really easy to integrate with Docker, so they didn't do it. And as HPC folks do it, they came up with their own solution, right? They leverage the containers that we provide, or the ecosystem we provide. And all of the runtimes out there today, they pull the image down that the scientist has from Docker Hub or a private registry, then they extract the file system, put it somehow on a shared file system that is connected to all the cluster nodes, and then they change root into the container file system. They iterated on the change root part, so there's more and more advanced now, but still that's basically the workflow that's going on. And one big thing is the workflow and the scheduling model that is used in HPC. That differs a little bit from what we see in enterprise IT. On the left-hand side, you guys are all familiar with Swarm and Kubernetes and how the Docker engine then creates processes, isolated and with namespaces and so on, so that you cannot use and utilize a shared system underneath. In HPC, it's a little different because you don't have a microservice that only runs on one node. You have a job that spans across multiple nodes, hundreds and thousands of nodes. You have to allocate a couple of nodes for a certain job. Let's say we have a job with 2 nodes in this case. And this job processes, and I have process 2 and process 2, that's slightly wrong, but anyhow. You have 2 processes that are scheduled by the agent. And what the agent makes sure of is first that no one else is using this node then, and also that the job processes can communicate. So the wire up of MPI, message passing interface, it's a library that's used a lot in HPC. All this wire up is done by the agent, and it helps to communicate across multiple nodes and utilize InfiniBand or OmniPass or whatever you have as an interconnect, so that you have this distributed job across multiple nodes running with very powerful hardware. And I have a little simple demo. Let me click here. No? Yeah, see, demo gods. Too bad. Here we go. Okay, so I have a little Docker file here, Docker Compose file, with etcd, which I use as a backend to configure all this stuff. But the important bit is here the controller and the worker. So I have Slurm control daemon, and I have a couple of worker daemons which are creating a little Slurm environment here. And if I jump into one of the nodes, and is it still the same name? Yes. I can do as info, right? And I have 2 pipelines with 4 workers, so worker 1 with worker 2, worker 4, which I can utilize for my HPC jobs. And what I can do, I can run just an interactive command, work hostname, which will execute hostname on the worker, and then it will provide me with the output. And I can scale this up, of course, to 4 nodes, which is hostname executed on all 4 worker nodes. So that's like an interactive, stupid job, right? If I want to run an API job, I can run an API job. Oh, let me first run it locally. And I have a very simple one, which I stole from the internet. Source. Hello. No. MPI. Hello. So this one just spins up the MPI domain, and it schedules this little job on the 2 nodes that I want to run it on, right? Or as many nodes as I want to run it on. And each process will just print which process number out of this job it is, and on which host it's running. So, and then it will just finalize the job. So let's run this bugger here. MPI run, user local bin, hello. So that, super easy. And I have this like this. So we see it runs on the same node because I'm not in a distributed setup, right? If I use allocate, if I use Slurm to allocate a job for me with 4 nodes, it will provide me with environment variables which specify which nodes I'm having. And if I do the same job again, then we'll see that it works, that it has 4 ranks now because I allocated 4 nodes, and it will run all the processes on different nodes. So we have like worker 1 to 4, and they have different problem of 4 nodes. That's that, and I can also use the batch system to schedule this. So I should have somewhere here, Slurm, job hello, or job ring. Job ring is simpler, it's a little bit more advanced than the hello one. It just sends an integer through all the ranks, and it will then, when this is decremented to 0, it will stop. So if I push this out a couple of times, yeah, it's already gone. So it's just this MPI run command will then be scheduled a couple of times on all the nodes. So that's a little Slurm setup. And we have to switch here. Here we go. Yeah, so and the current solution, and I talked about MPI runtime, HPC runtime, sorry, which are on the market or in the community. They are basically a little wrapper around the job process. So you put the HPC runtime command in front, and it will just wrap the process into whatever runtime you choose. But it will not interfere much with the workflow that everyone uses. Like what I just showed, this MPI relies on either SSH or PIMX. I don't want to go into the details. So it's a drop-in replacement of the current model anyhow. So that's very simple to adopt. That's why it gained some traction. But the problem is that it's not OCI compliant, so you cannot run it with Kubernetes. You cannot plug it into other schedulers, and it's more likely it's like a snowflake solution for HPC communities. And I think, being an HPC guy myself, we had a lot of. I have to be careful how much I emphasize this, but we had a couple of failures over the years where we tried to create something and then it never went off, and then we stuck with this solution. And we were not able to utilize all the cool benefits stuff that came out of the enterprise IT or cloud systems. So it's not OCI compliant, and it does not integrate with the upstream ecosystem. And so such like secured supply chain, which you heard a lot of about in the DockerCon, I guess. And so all the cool stuff is not really working. So let's talk a little bit about the challenges. There are 2 challenges actually that we need to focus on and that we need to fix, and then we are good for the first iteration. First one is kernel-bypassing devices. So with the web server that just uses a TCP IP stack of the kernel to communicate over Ethernet, that you can utilize or that you can containerize very easily, right? Because you utilize the kernel and the lib network in the container, and you are fine communicating. Within HPC, you use kernel bypassing, which means that you have the driver in the user land of the application and it directly communicates with the network card, or maybe more known with the GPU. It's the same model, right? You don't have much kernel stuff that is in your way to slow down your computation or your networking capabilities. But since Linux containers or containers in general, they rely on the kernel functionality, that's a problem for containers, right? And up until now, or recently, let's say, the ecosystem in container land was host agnostic. So you don't want to know what's down there. You don't want to map in GPUs and try to schedule stuff where you don't know whether the device is there or not. So all the ecosystem as of today is mostly host agnostic, so that you do not know and you don't want to know what's underneath. You just want to schedule your workload so it works everywhere. So that's one piece. The other piece is that in scientific environments, you need to match the assumptions that the end user has, right? And the end user at an HPC site logs into a system and sends a job to this batch scheduler, and he does not know in advance where the job will end up. It could be on the newest system, it could be on the older system. The older system might have different hardware or different mount points or what have you. And so this has to be abstracted away from the user. So you cannot just do Docker run and expect that this Docker run command will work on all the other nodes, right? So we need to make sure that the engine or some component is capable of doing a little bit of decision when the job is really actually scheduled. And one thing that we need to do is this device stuff, but also shared environments, shared file systems. So you want to map in the complete home directory, for instance, or you want to map in a Scratch file system or a project dir into the container, and you want to rely on the Unix, the POSIX group and user permissions so that users cannot really interfere with stuff that they should not see and they should not interfere with, right? So that's a challenge that we need to adopt and that we need to tackle. And that's all, it's not rocket science. Let's look at the stack that you need to utilize when you want to run, for instance, NVIDIA devices here. You can specify devices within the client, so you do docker run -- device. This will end up as a Docker object within the engine. It looks like this. And when it's hands down to containerd will create an OCI runtime spec, which is then fired off by runc, and so you can use the GPU. NVIDIA does it a little bit different with NVIDIA Docker, so they had a lot of pressure because they have this fancy, expensive systems. They needed to do something, and they gravitated towards an idea where we have a binary that is executed as a pre-start hook, which means the container is created, so your Docker create is executed basically, and this little hook is executed within the namespaces and the file system of said container before the process is started. So then you can do kernel module configuration and you can map in the devices, and this is the binary that they used. Michael did a little PR the other day, like a couple of weeks ago, which is implementing containerd or enabling containerd to interact and use GPUs as a primitive within containerd. So we are like talking about it internally, how to put it and where to put it. And what I did during a hack week, like months ago, I created a very crude hack because I'm not as good in Go as other people. I just created a little weird hack in the engine where I just override the Docker run arguments or the arguments of the Docker run API call so that I can say, I want this mounts in every container, I want this devices in the container, and I can inspect the environment of the container so that I can decide how many devices I want to add in and so on. So that's a very nice crude hack, I think, but it's of course not what we will end up with. But it just shows that everything is possible, we just need to decide where to put it. And that's called Houdini plugin because it's magic. You have a little configuration file on the host where you can provide default mounts, default environment variables, and so on. And I have a little demo of this as well, though we are sharp in time. Okay, so this is the P2 box up in in AWS with 8 GPUs, and if I would run the NVIDIA SMI command, then we see all the devices. What I rather do is I put this in the container and see what's happening. So with this label, I can trigger my Houdini plugin to do stuff with the container. And what we see here is that it sees only one GPU. Why is that? Because I provided it with the default environment variable of NVIDIA visible devices 0. So it only sees the first GPU. And another important thing, as I said, is shared environments. If I want to touch something in another user's home directory, this of course is not possible. So I'm here, the user Docker with the user ID 1000. And if I want to touch something in this user's home directory, of course I cannot do it. And if I use Houdini, as you see here, I have this user configuration where I just pin every user to, or every process within the container to be run under user ID 1000 and group ID 1000. So if I do the same thing with the Houdini plugin in the mix, and I even want to be root here, then this will result in the same, the same outcome. Like I am not able and allowed to touch this file there. And if we combine those two, I have a directory here, data. If I run, for instance, Keras, which is an API or like an abstraction of different deep learning models, I can run this, and it will download the data set and puts it into this home Docker data directory, and then it will run 2 iterations of the simulation or this deep learning network, and will then exit. And when this finishes, we will see that this mnist file ended up in my data directory, in my home directory with my user and with my group. And when I run it again, I can access this input file and be done with it. So let's just prove it here. Ta-da, magic. And it has the user ID. Docker and Docker. So with this, you can just map in complete file systems and be safe so that everyone can use the thing. Okay, let's switch back. And we are...
Great.
Okay, cool. So that's a Houdini plugin. Opportunities.
Yeah, so now you can see we haven't fully baked in a HPC solution into our product yet, but we're figuring out where to put it, what's the best way to go about it. And then we have Christian's hack that kind of acts as a go-between right now. But what we're really thinking about is how everyone can leverage HPC in the enterprise. So what you're looking at here is our standard Docker build, ship, and run. So oftentimes, even HPC sites, they have standard web services that they want to run and manage. So what we want to see is the ability to manage all of your workloads from one central place. The keynote talked about being able to have federated management across cloud providers, and that ties into the workload type too. So we envision, a world where you can manage your HPC workloads, traditional applications, third-party COTS, all in your enterprise edition. So being able to leverage secure software supply chains, being able to sign the images that are moving through your system and scan them for vulnerabilities and create policies around those, but having a strong governance model to manage your users. So Christian's going to talk a little bit about the convergence of high performance computing and artificial intelligence, but ultimately this is not going to just be a scientific use case. This is going to expand into business problems as well. So something that we really want to support and get everyone ingratiated in as soon as possible.
Yeah, and with this slide, or with this couple of slides, we just want to stress the fact that there's a convergence going on between big data and big compute, or AI and HPC, or whatever you call it. We have the current use case of non-GPU containers, so we cannot use GPUs as of today. That's easy. If you want to start with GPUs, and this is what is supported by all of the runtimes today, is you can have a single node and you can have local storage. You just need to pass through the device that I showed with my little plugin as well. You can do that. It's pretty simple, but it won't get you extremely, or it will get you started. But if you want to thrift through 50 gigabytes of cat and dog data, you need to somehow access those data, those pictures somewhere. And this is where the intermediate step begins, right? You have a single node, but you have shared file systems, and you want to access data on the shared file system, honoring the POSIX user permissions. And this is where we need to allow shared file systems and shared environments to be able to be used with this system. So you need to pin the user, as I showed, and this, of course, has to be dynamic, depending on what user wants to run this container, and he shouldn't be able to override this. And once you fix this, once you leverage all your GPU power on a single node, and you need to run on multiple nodes to be able to fit this model into a distributed job, you need to go and use MPI and exchange intermediate results between multiple nodes and use shared storage. And this is the kicker now. This is called HPC. So you have MPI, message passing, you have a shared file system, and you have a couple of nodes working together to solve a problem. And this is an HPC job. So that's why we want to push forward and stress that we are not going to fix only the beginner problem. We are aiming to fix all the problems. So we want to fix the intermediate and the advanced problem so that we can even support HPC use cases. And this is where JPU and HPC will meet in the future. And not that you have to trust me on this. There's a nice study from Thorsten Höfler from the ETH Zurich. He put out there that the trend is going towards GPUs, of course, because they are available a lot and they're cheaper than special things. And the trend is also to go multi-node. So this jobs are going multi-node more and more. As I said before, this NVIDIA box costs you like almost 500K or 400K. And you might be able to do the same computational power with commodity hardware where you have 20 nodes costing you maybe 15K. And so you end up with 300K, but you have a much more flexible system. So this is where I think we should go to. And there are a couple of conferences I'm going to be, or we will be. So there's the ISC in Frankfurt. I think that's the main one in 2 weeks. I will be there the whole week. So if you attend the ISC, so ping me and we can have a chat. There's an HPC workshop at the end of the ISC, a full day on the 28th. So you should sign up and join this as well. It's going to be fun. And we will be at the HPC Advisory Council workshops most likely. And of course, the SC 18 in November in Dallas. We will be most likely there as well. And hopefully the DockerCon Europe. So you guys should come over to Europe. We will talk most certainly about GPU and HPC there as well. Okay?
I've been waiting a year to show this slide, so I'm really excited about this. But basically, we want Docker to do for science what we did for developers. We really believe that it can create, greater innovation, make it easier to use. It's something that we think is really important. So we're very excited to keep supporting it, and any feedback that we can get from you all will be very helpful. So thank you.
Awesome. Thank you.